Hello boys and girls, welcome to Jabulani's Playhouse. I'm Jabu and I'm Lani, and today we're going to start looking at mechanics, gears and worm drivers, right? We sure are. This is by Engino again, Play to Invent, and we're discovering STEM, so that's science, technology, engineering and mathematics, right? It sure is, and this one has 12 models to build, right? 6 online and 6 printed instructions, and like always, we're going to start with the printed instructions, right? We sure are. And by the way, boys and girls, it's very hot here in the house, so we don't have air conditioning, do we, Lani? No, we don't, Jabu. So we've got the windows open and maybe you can hear the birds chirping outside, right? That's right. I hope it doesn't disturb boys and girls at home, but it makes it a little bit more comfortable for us to do the videos, right? Hehe, that's right. Let's get to it. You betcha. So there's an overview, boys and girls. Mechanics, gears, and worm drivers. This is going to be very interesting. If you've been following along with us, you know all about these toys so far. And on this one, we're going to learn how gears can easily reduce or increase speed, change force, or transfer motion from one position to another. Discover how worm drives are used to greatly reduce rotational speed. And that's about how things turn around, right? Rotation is how things turn in a circle. Our greatly reduced rotational speed and how screws can convert rotational motion to linear motion. So basically, when you have a screw, it goes from rotational or circular motion, and then it can help cause something else to go in a linear motion, which is a straight motion, right? That's right, Jabu. While greatly increasing force. Build 12 working models such as an experimental crane, a gearbox, a carousel, a helicopter, that'll be fun, a screw press, and a crane with a rotating arm. You can find easy to follow building instructions for all models either online or in the booklet included. The booklet provides detailed explanations of the different scientific principles applied and incorporates innovative experimental activities for hands-on learning. A quiz section is also available to challenge your newly acquired knowledge, and we know that from all of these before, right? So there you go. You can see 16 pages of theory and amazing facts, 6 pages of experimental activities, 3 pages of revision quiz, and 17 pages of step-by-step instructions. Now what's this one, I wonder? This looks like, this could be a helicopter, I suppose. Could be, Jabu, I'm not sure. We'll have to find out, hey? We sure will. And there's 6 online, 6 printed, 8 to 16 for boys and girls ages 8 to 16. Get a working vise, crane with a rotating arm, a helicopter. This is the helicopter here. And also a hand drill, as you can see here, boys and girls. So I'm not sure what this one is. I guess we will find out. Some information here. You can pause the video to read about that, the purpose of STEM education, which is very important, but so are the arts and language, right? Of course, Jabu, everything is important. You betcha. So here we learn how gears can easily reduce or increase speed. That's a little bit of what we've read already. And these toys win lots of awards, as you can see, boys and girls. Aha! Here's a whole bunch of the different toys you can build. There's the drill. There's the helicopter. Not sure what these ones are. That's like a platform, I think. This one, not so sure. There's some more info. You can always pause that if you want to read it. Let's take a look at the back. Aha, an overview of the back. Mechanics. Gears and worm drives. Let's read, Lani. Ancient civilizations used gearing technology to construct machines and devices that even today puzzle scientists by their complexity and precision. Some of these devices were able to calculate the movement of planets, moons, and stars, making accurate predictions that even match modern-day computers. Wow, Jabu, that's very clever. I know, they were very clever back then. Similarly, screws and worm drives were also used in antiquity to multiply force and change the direction of motion. A worm screw is actually an inclined plane wrapped around a cylinder. Nowadays, gears and worm drives can be found in a variety of shapes and sizes and are used in many machines and constructions, from home appliances to car engines and airplanes. So enter the fascinating world of gears and worm drives and explore the magic of STEM. Yay, Jabu! It tells you a little bit about this set. Includes an activity book with innovative experiments and detailed explanations of the different technological principles applied. And again, we won't read the whole book, but we will take a look at each page. You can pause the video then to read what the information is on the page if that's what you want. That's right, Jabu. Build a hand drill. The industrial drill can be used for drilling or screwing and is usually powered by electrical energy. This Engino model demonstrates the more traditional technique of hand-driven mechanisms and how speed can be increased to a greater extent by the simple use of gears. Build a helicopter. This helicopter has high-speed rotor blades powered by 2 crown gears with a high gear ratio. The gears are used to change the direction of motion from horizontal to vertical, while motion is transferred by a series of interconnected shafts. That's very clever, Jabu. I know it is. Build a crane with a rotating arm. Follow the instructions to build a model of a crane with a rotating arm and discover the relationship between the worm drive's characteristics and the gear's revolutions. Learn about the usefulness of the ratchet mechanism and how it works. Aha, these are the ones we didn't know about. Build a folding platform with a screw. The folding platform model uses the Engino worm as a screw similar to the Vise model. It converts rotational motion to linear and pushes or pulls the scissor type linkages to raise and lower the platform. You see? So there's the rotational motion of this little gear here, or screw, and you use that to create a rotational movement going in circles that will create a linear motion up and down of the platform, right? That's very clever, Jabu. Yeah, it is. Do you want to read this one? Build a carousel. A visit to the playground excites both children and grown-ups. Build this model of a fully functional carousel and see how you can rotate the seats at very high speeds. Observe how the seats move higher and higher as they rotate faster and faster. Exactly, that's a lot of fun. We've been on one of those, haven't we, Lani? We sure have, Jabu, and it was tons of fun. You betcha. Okay, so we've got a bit of tape here. We need to just cut through in order to open this up. There we go. Now let's see what we've got inside here, Lani. Okay, there's all our goodies. Wow, lots of goodies in there. Dump them out and have a look. Okay, so this kit has got oranges and grays and blacks and whites, I think, and different shades of grays. There's 1, 2, lots of gears and pieces here. 3, we've got our little extractor as well. So there's 4 bags, Lani. Wow, Jabu, that's great. Yeah, excellent, okay. And here's the booklet as we've seen before. So maybe before we get going, we'll take a moment to go through this booklet. This is probably the same information that's on the box, so we don't need to go through that. You can see there's lots of good information in these booklets here. They really help a lot. So let's take a look, take a moment to read or to pause on each of the pages so the boys and girls can read it as well. So we start the building instructions on page 28 and we start with the experimental crane. It's going to be fun, Jabu. I love it. There's the experiments you can do and the theory. If you buy this toy at your local toy shop, it's a lot of fun. You get a lot of use out of these because they're very clever, aren't they, Lani? They're very clever, and they get 12 toys that we can build, right? Exactly. Okay, so there's theory. This is what we will learn. Well, bicycles have a special mechanism that helps us to transfer power from the pedals to the wheels. Pendulum clocks contain something similar, which allows them to tell time with great precision. So this Discovering STEM Gears and Worm Drives contains a comprehensive theoretical section with building challenges and interesting facts. Got the history of gears and worm drives. Large gears were used during ancient times, first by Greeks and then by Romans in their water mills. The Greek philosopher and scientist at the time, Archimedes, designed an ingenious device, the odometer, which could measure the distance traveled by a carriage based on the wheel's revolutions. And we know we have odometers in cars nowadays, right? Tells you how far in miles or kilometers you've traveled. Exactly, it's very clever. Wow. And he developed that probably, I don't know, 1,000, 2,000 years ago? A long time ago, hey? The Antikythera mechanism was a very elaborate machine that was able to do calculations of astronomical positions using a complex systems of gears. Early wooden screw-shaped tools became common in the 1st century BC and were used in wine and olive presses. Wow, Jabu, I didn't know that. I know there's lots here that we didn't know, hey? Nowadays, the concept of Archimedes' invention is applied to high-speed tools and various machines for drainage, irrigation, and oil extraction. Did you know Leonardo da Vinci designed the first helicopter called the helical air screw? It consists of a platform with a helical screw in its center and wings made of a rough cloth for moving the helicopter in a vertical direction. Unfortunately, the helicopter was never put in use, but a model has been built at the Museum of Science in Boston. I wonder if it works, Jabu. I know, me too. There's a definition of a gear. Gears are wheels with teeth around their circumference, enabling them to mesh with each other. They belong in the category of simple machines, which means they can increase the applied force and have mechanical advantages. Gears can be found in almost all machines that have moving parts, and we use them if we want to transfer motion, reverse the direction of rotation, increase or decrease the speed of rotation, change the axis of rotation, decrease or increase the force of the machine. A gear isolated cannot really do anything and has to be connected with other gears in order to transfer power. The teeth of the gears are the most essential elements, and their design will determine the efficiency of gear transmission. Gear terminology. The ideal profile design allows the teeth to mesh while touching only at a single point. As the gears rotate, the teeth should move as they were rolling on each other instead of sliding. This diagram shows you how. Here's some examples of gear use, Lani. There's a car gearbox transmission, Jabu. I know, wow, very complicated. And then inside view, a portable music player and gears in a wristwatch, which have been probably magnified. Then there's a chain drive. The gear setup is very similar to pulley systems, another simple machine. I think we've done pulleys before, haven't we? We have, Jabu, that's right. There's another important difference between gears and pulleys. If you look at the red arrows in the picture of the connected gears and pulleys of these pages, you will notice that they have different direction of rotation. Two meshed gears rotate in reverse, while two connected pulleys rotate in the same direction. Wow, Jabu, that's interesting. Yeah, because you see this goes this way. You can see this goes that way, turns this way, and the small one also turns that way in the pulley system. But in the gear system here, see the big one is turning this way, which is pushing the other one in the opposite direction. Ah, very clever, Jabu. Did you know the unicycle is a single-wheel vehicle that entertains circus audiences and hobbyists? We've seen clowns at Cirque du Soleil riding on those. Hey, I know, they're very silly, very funny. Okay, physical laws. Circumference. In order to calculate the circumference of a circle, we can take a piece of string and wrap it around a gear. The resulting length of the string, measured by a ruler, is the circumference of the circle. So the circumference of a circle is how long it is to maybe walk or measure the outside of a circle, right? And then it says if we divide the length of the surrounding string of each gear with the diameter of this corresponding gear, we will find a number between 3 and 4. As a matter of fact, if you measure any circle, you will always find the same number, which in mathematics is shown with the Greek letter pi, and is approximately 3.14. And the interesting thing about pi, Lani, what's that, Jabu? Is that it doesn't repeat. So these digits behind the point, like the 0.14, they carry on infinitely, never repeating the same pattern. Wow, Jabu, that's a very interesting number, isn't it? It's a very interesting number. I think mathematicians are very inspired by it and curious about that as well. Velocity ratio. We have found above that a relationship exists between the diameters of the meshing gears, the circumferences of the gears, and their number of teeth. When designing machines with gears, it is very important to be able to calculate the speed and torque of the output shaft. Such calculations are based on the gear ratio, or as it is more generally called, velocity. The velocity ratio can be found by dividing the speed of the drive gear with the speed of the driven gear. This is very complicated, Jabu. I know. Let's move on here and see what else we can find out. All simple machines are power converters, meaning that they transform speed or power accordingly. We can see this with gears if we examine the example of the bicycle. As you know, all modern bicycles allow us to change gear, and we can either ride fast or slow. When we are driving on a straight road or downhill, it is quite easy to move, so we change gear to pedal slower and drive faster. This happens because our weight does not feel very heavy due to gravity, and all our power is converted to speed. When we're driving uphill, our weight feels much heavier and we cannot go fast. In fact, if you have experienced this, you will know that the only way to move forward is to change gears so that we pedal faster and move slower. Our power is now converted to torque instead of speed. When we connect gears in such a way as to increase speed, we are losing torque, which means the ability of a force to rotate an axle. I see, Jabu. What we gain in speed, we lose in torque. On the other hand, when we connect gears in such a way as to increase torque, which means the speed, or the force, the ability of a force to rotate an axle, we connect gears in such a way as to increase torque and have more strength. We are losing speed. What we gain in torque, we lose in speed. So they're related. I see, Jabu. So torque is the ability of a force to rotate an axle. So when we gain in speed, we lose in torque. And what we gain in torque, we lose in speed. So in torque, when the force to rotate an axle, which is the torque, is easier, which means when you're climbing up a hill, your legs can pedal around faster around the axle. That's the torque. So the torque is easier because there's not as much force required, then your speed goes down. And when your speed goes up, then torque becomes harder, right? I see, Jabu, it's very complicated. I have to concentrate on that. I know, it takes a lot of study to understand this, but that's okay. That's what school's for. Did you know the mathematical constant pi comes from the initial of the Greek word something or other, which means circumference. Studies on the pyramids of Giza have found that the ratio of a pyramid's perimeter to its height is double pi. Very interesting, Jabu. Building challenge, high-speed fans. Summer for many is the best season of the year, with lots of sunlight, swimming in the sea, and eating delicious ice creams. But what happens if the temperature becomes too high and the air condition is broken? Which is what we're experiencing right now. That's why I got the windows open. Exactly. People often use fans in order to cool down. And we're going to build a fan too. That's going to be fun, Jabu. It sure is. Types of gears. There's an idler gear, which sits in between two gears. Compound gears, which I guess are two or more gears together. There's a gearbox inside of a clock. Very interesting. All sorts of different gears, eh? Fascinating, Jabu. Rack and pinion. Rack and pinion, some of boys and girls might know, is often related to steering wheels in cars, right? Exactly, Jabu. In many machines, there is a need to convert rotational motion to linear, that is, in a straight line movement. Other machines can do this as well, such as the crank or the cam, even linkages. However, gears can do it with precision, allowing full control at any position. These gears are called rack and pinion. The rack and pinion gear system. So the rack is, I guess, a straight-toothed piece of metal, and the pinion gear sits on top of that. I guess we've got an Engino rack and pinion gear system. There's the sorts of other gears, spur gears, non-circular gears, rotating signpost. I guess we'll build a rotating signpost. Did you know another gear setup that can have special applications is the planetary gearing, also called elliptic gearing. This is a complex setup of gears that consists of one or more outer gears called planet gears revolving around a central gear called a sun. If you see in the picture below, there is also an outer ring called annulus, which meshes with the planet gears. A great advantage of this type of gearing is that it is compact and can transfer big loads. Wow, Jabu, this is very fascinating. It is, isn't it, hey? Changing an axle's direction. So that can be done too inside of a motor transmission. There's an Engino hand blender that we will be building as well. That'll be fun. Definition of a screw. A screw is simply a cylinder with a thread at its outer surface, also called a helical ridge. Screws can have a flat or a pointed end and are categorized according to their application. The most common use of screws is as fasteners, enabling connection of different materials. However, screws can also be used in conjunction with a nut or a tapped hole. When the screw rotates, it moves through the nut, which has the same internal threading, converting the rotational motion to linear. that is in a straight line. Screws are the basis of worm drives, which we will examine later on. There's a folding platform with screw which we'll be building, so we'll learn about that. Did you know throughout the centuries hand drills have been improved in order to become more user-friendly? The ancient Indians and Egyptians used anchor drills to pierce gemstones. Nowadays, electric hand drills offer accuracy and speed. When fastening thin metal plates, there is no need to make a hole first and then pass the screw. This is done at the same time as engineers had the innovative idea to combine drill bits and screws, creating an invention called self-tapping screw. Very interesting, Jabu. Yeah, it is, Lani. Here we learn about types of screws. Standard screw, screws with a nut, a set screw, drills is a type of screw. Hand drill we'll be building, size of screw pitch. A manual hand drill, and the bottle opener is actually a screw. Head shape. There's a bunch of different head shapes. That's a slotted head screw here. And then all these other ones, slotted, hexagon, Robertson's, and a square head. Wow, Jabu, I know. A countersunk head screw sunk in wood, a raised head screw, and a round head screw down here. Did you know the ship's propeller is actually a screw? Wow, that's cool, Jabu. I know, I guess it screws through the water, creating linear motion, right? Tools for screws. A crosshead screwdriver, a slot head screwdriver, a battery operated screwdriver, an Allen key is also used on screws. Spanners can be used on screws. An adjustable wrench as well, a ratchet set. Mechanical advantage. Screw as an inclined plane. Interesting. This gets technical here, so if boys and girls want to read that, they can just pause the video for a moment. There's a vise. I guess we're going to build a vise too. Wow. Worm drives. Another application of worm screws is that of being the tuning mechanism for many musical instruments, including guitars. I'm familiar with that, Jabu. I know. Ratchet mechanism. Very interesting. This is complicated here. We'll let the boys and girls pause if they want to read. There's a crane with a moving arm which we'll do. This will be fun. And here is learning about gears and worm drives. The boys and girls look through this if they want. Very interesting. Wow, lots to learn, Lani. There is sure a lot to learn here, Jabu. Wow, this is a long booklet. Now we're halfway through it, hey? Yeah. Getting close to where we're going to start building, I think. That's my favorite part. I know, because we're just puppies, so we don't really understand all this human stuff about worms and screws and gears and stuff, hey? That's right. And here's the quizzes. The boys and girls want to try their hand at the quizzes. Some more quizzes, and then we're going to get started on the experimental crane, which we're going to build next time, right? That's right, Jabu. Okay, there's an experimental crane. How many pages? 1, 2, 3. It's 3 pages, so it might take us a couple of videos. We'll see how we do with it, hey? Sounds good to me, Jabu. Thanks for joining us, boys and girls. Love to have you along. We're learning mechanics with gears and worm drives. So come on back, we're going to start building, hey? Yeah, that's right, Jabu. We miss you when you're not here. We're going to enjoy it, aren't we? We sure are, because we love this stuff, hey? We do, and we learn some stuff too, hey? Exactly. So I'll see you next time, boys and girls. Bye-bye for now. Bye-bye.